The first few sections of the course are definitely review. They're things I know you've seen before, but oftentimes you need a little bit of reminder about them. And they are fairly important because in later chapters, we're going to go ahead and assume that this is common knowledge, and that working with things like exponents and radicals, for example, in this first section, are a given. And so, you may find that the first few sections go a little bit slow, and you may be bored. If you're not, that's fine. That's great. But just be aware that those sections are important for later sections, and we're going to build on those things. So the first thing we're going to talk about are exponents and radicals. And the first thing that we're going to talk about are exponents. And basically, we're going to eventually relate everything back to exponents. And so the thing on this page is the overarching important things in this section. So let's remind ourselves what an exponent is. So if we have a number, if a is a real number and n is some integer, so some other number, then the nth power of a is what we get when we multiply a by itself n times. And so you see a is being multiplied by itself n times, and we write that as a to the n. And so quick examples of that include if we have 2 squared, right, that's the same thing as just multiplying 2 by itself. If we had 3 to the 4th power, that's the same thing as multiplying 3 by itself 4 times. And of course we could do it with variables as well. So if we had x cubed, x raised to the 3rd power, that's just x multiplied by itself 3 times. Now that's probably something that you're familiar with. And the real thing that we want to be careful about is what we do when we have things that are variables that are raised to an exponent. And a very common mistake that people make is when you have variables, or it doesn't have to be variables, but 2 things that are being added inside of parentheses, and let's say that's being squared. This notation means the same thing it did in the previous 2 cases, where we simply just want to multiply x plus y by itself. Right? X plus y squared just means multiply x plus y times x plus y. Right? Using the same idea as above. The thing that you want to be careful about, though, is people oftentimes want to write this as x squared plus y squared. Right? It kind of looks like you can take that square and distribute it into the parenthesis and get x squared plus y squared. And I just want to say right up front that this is not true. So if you have 2 things being added and you're squaring them, you want to do the parenthesis multiplied by itself, which is going to involve foiling. And so this is a very common error, and I'm going to harp on that throughout the semester here. A few key properties of exponents are the ones that are shown here. So if we have a number raised to the 0 power, it doesn't have to be a number. Anything raised to the 0 power is 1. So examples of that include 4 to the 0 power, that would be 1. It could be any number, though, so we could do something like pi to the 0 power. Right? Pi is a number, and so pi raised to the 0 power is also going to be 1. And we can do anything raised to the 0 power being 1. So let's do x plus y again. Let's say we have x plus y inside the parentheses again. If we raise those parentheses to the 0 power, we get 1. And so any conglomerate of things being added, subtracted, multiplied, or divided, doesn't matter. If they're all raised to the power of 0, we get 1. So that's a key property of exponents. The other property that we're looking at here is what happens when we have a negative exponent. And so this is showing us that if we have something raised to the negative n, where n is a positive number, then that's the same thing as changing this relationship into a fraction, 1 over n. So if we have something like 4 to the minus 1, that's the same thing as 1 over 4 to the 1, or 1/4. But it goes both ways. This relationship works both ways. So if we have something that is a fraction with an exponent in the bottom, then we can rewrite it as not a fraction. So we can go from the right side to the left side by making it a negative exponent. So for example, if we had 1 over x squared, we could also think about that as x to the minus 2. And that's also true. Just realizing my lighting's a little bad here. I'm trying to fix the lighting here. That's a little bit better, I think. And again, the same thing applies if we have a bunch of things being added or subtracted. So let's go back to some variables. Let's say we had x minus y inside parentheses, and that entire parentheses is raised to a negative number, like -6, say. Then we could take that entire parentheses and write it as 1 over x minus y to the 6. And again, if we had something that looked like 1 over x minus y to the 6, then you can rewrite it as not a fraction using a negative exponent. It depends on what you want to do, but the relationship works both ways. Now, how do we deal with exponents? How do we combine them and use them in practice? That's what this next box is all about. There are 5 main properties that tell us what to do with exponents. I'm going to zoom in a little bit. So, I forgot we can't zoom while recording video, but take a look at your own paper if it's a little bit too small. The first property is saying if we have 2 numbers that are raised to different powers, and the 2 numbers are being multiplied, then we add the exponents. And there's a very clear example of that right here. 3 squared times 3 to the 5th. We've got like bases here, right? The base is both 3. Different exponents. You add the exponents. So we keep the base of 3, and then we add the 2 and the 5 to get 3 to the 7th. If exponents are being divided, if 2 numbers are being divided, so a to the m divided by a to the n, again, like bases, different exponents, then we subtract the exponents. So if we had 3 to the 5th divided by 3 squared, they both have a base of 3, so we keep that base of 3, and we subtract the exponents, the number on the top minus the number on the bottom. The third example is what we do when we have a power raised to a power. So this is a number raised to the power m, and that is being raised to the power of n. In that case, you multiply the 2 powers. And so if we had 3 squared raised to the 5th, then we take the 3, we keep the 3, and we multiply the 2 and the 5 to get 3 to the 10. So number 1 and number 3 are the 2 that oftentimes people confuse and usually use one in the other situation. And so just notice the difference, right? In the first one, we add exponents when we have a like base being multiplied together. We multiply exponents if we have a base that's a power raised to a power. Right, so try to be careful about the difference between those 2. The third property is a distributed property. It tells us what we do when we have 2 numbers or 2 anything inside of a parenthesis. Could be variables. They're both inside the parenthesis and they're both being raised to the nth power. And so in this situation, you take the n and you distribute it to both numbers individually. So the n goes to the b and it goes to the a, and we end up with a to the n, b to the n. Just like this example here. 3 times 4 squared, we get 3 squared times 4 squared, right? You just take that 2, you distribute it through there, and we get it on both terms. Now I want to compare this one really quickly to this one up here that I told you not to do before, right? Up here, I said, be careful about this example because lots of people usually want to take the square and distribute it, and you can't do that. And here, it looks like I'm telling you to go ahead and distribute the square. And so I want to point out that the difference is that the numbers inside this parenthesis are being multiplied, which is what allows us to distribute the exponent, where the number inside here, the variables, are being added, right? So this plus sign is the difference between this example and this example where they're being multiplied. If they're being multiplied, you can distribute the exponent. If they're being added or subtracted, you cannot. All right, that's the difference there. And then the last example here, the last property is also a distributive property. It says if we have 2 things being divided and they're both raised to a power, then we can take the power and distribute it inside there as well. So 3 fourths raised to the 2nd power, we can take the square and distribute it back through and get 3 squared over 4 squared. Now we want to use these properties to simplify equations, simplify expressions. It comes up quite a bit. These are some toy examples that don't have too much meaning, but they do a good job of getting you to practice these properties and really getting a good grip on them. And so before I go ahead and do some of them, let me just say that there's more than one way to approach them. You might think about doing them one way, and your friend might think about doing them another way. And as long as you're following these properties carefully and correctly, you should be able to do them either way. And so that's a really nice thing about this. Also a little bit tricky because it's sometimes not clear what to do first. But as long as you're following the properties, you can do them in different orders. So the first thing I'm going to do in this first example here is inside each parenthesis we don't have any like bases, right? We've got an a and a z in both of them, and so I'm going to go ahead but they're both being multiplied together. Both those parentheses are being multiplied, and so I'm going to go ahead and drop the parentheses and just multiply everything together and group things with like bases. So I'm going to group the numbers together. I'm going to group the variables that are the same together. And then that lets me see which properties to use, because now they're all grouped together, and now I can make sense of some of these properties up here. So now when I'm looking up at the properties, it looks to me like they're mostly in property number 1, law number 1 here, right? We've got like bases raised to different powers. So we've got like A's raised to different powers, like Z raised to different powers. And so I'm going to use law 1, so this equals by law number 1. Well, first thing, we can multiply the 4 and the 1, or the 8 and the 1/2 together to get 4. But then I can take the like base and use law number 1. So I have A to the 2 plus 3. We add those powers, and then Z to the 1 plus 4. And so this simplifies down to 4A to the 5th, Z to the 5th. And we can't do anything else because these are different bases. We can't add those powers together because this is a base A and this is a base Z, right? Look at the law here. It has the same base in both those cases. And so it has to have the same base in order to use the laws. Okay, that's a good first one. Let's take a look at the second one here. We've got a fraction here, so it looks like we're going to eventually want to use number 5. But before we do number 5, it looks like we're going to want to use number 2 eventually. Excuse me, but in number 2, we've got individual numbers raised to powers, and in this one, we've got a parenthesis raised to a power first with numbers raised to the powers inside of it. And so we need to get rid of the parentheses, in other words, first. And so there's another law we need to use before number 2, and that law is number 4, because here we have numbers inside parentheses raised to a power, and here we also have numbers inside parentheses raised to a power. So the first thing I'm going to do is use law number 4 to distribute the powers inside of the parentheses. And so when I do that, I'm going to write out all the details here. We'll get u to the minus 1 raised to the second power, v squared raised to the second power, u cubed raised to the second power, and v to the minus 2. I'm sorry, this is the third power, so this one should be a 3. And v to the minus 2 also raised to the third power. So I use minus law 4, and that's good. And now I've got powers raised to powers. And so now in this situation, it looks like we've got law 3, right? I've got powers raised to powers, just like law 3 says, and law 3 says you multiply the powers. And so in the next step, I'm going to use law 3 to multiply the powers. So we'll have u to the minus 2, v to the 4th, u to the 9th, and v to the minus 6. And there's at least one more step to do here. Now we're ready to use number 2, because now we have like bases, like u, raised to different powers, and they're being divided. So now this looks a lot like property number 2. And so now we can use property number 2 to subtract the powers. But we need to be careful, because we've got some negative exponents, and so when we subtract negative exponents, we just need to be careful about that. So we're going to use law 2 here and subtract the powers. So we'll have u to the minus 2 minus 9, and then be careful with the second one because we've got a negative down here. So we have v to the 4th minus minus 6. And so that double minus is going to turn into a plus. That's why we just need to be a little bit careful about that. And so those simplifying further, we get u to the minus 11, right? Minus 2 minus 9. And then when we do 4 minus minus 6, we add them to get v to the 10th. Now we've combined things down to single bases, but a very common thing to do, sort of the rule of thumb, is that you never want to leave a negative exponent. We always want to write exponents in the positive form. And so we want to get rid of this negative 11 by using this property up here. If we have a negative exponent, we can change it into a fraction. And so we're going to get rid of that negative 11 by writing it as a fraction. And so this is going to be v to the 10th divided by u to the 11th. Now we've got single bases raised to a power, and they're all positive exponents. And so that's a good place to stop on that one. At this point, let's see, should I do one more maybe? Maybe I'll do one more and then ask you to try one. Throughout the course, I'm going to ask you to try problems as we go. I think it's a really, I know, it's been a proven fact. It's not my opinion. It's scientifically proven that if you work through problems as you're learning them, it makes you better at that particular concept. Even getting the problem wrong is actually beneficial to your learning. And so throughout the course, if I pause for a minute and ask you to try some problems, it's a really good idea to do that. I certainly can't make you do that. I'm not going to try to make you do that, right? You have to be, the sort of the owner of your own course here and decide what you want to do. But if you try the problems as we go, it's really, really helpful, because if you get it right, it means you understand it, obviously. And if you get it wrong, what happens is I'll go ahead and write down the right answer, and then you correct it mentally, and you won't make that mistake again, and you learn it. You have a much more solidified learning process that way. So anyway, I'll do one more. I was going to do this one down here, and then maybe ask you to try the one on the right. So on this first one here, we want to identify what's going on. So first of all, we've got a division problem inside the parenthesis. I'll just smudge this here. Let me go ahead and get rid of that smudge. Well, I won't get rid of it because I'll have to white out over it. You can see your own paper what that looks like. Anyway, we've got a division problem inside the parenthesis, but the point is we've got a parenthesis first, and it's raised to a power. And so the first thing we want to do is use laws number 4 and law number 5 to distribute the -3 inside the parenthesis. And so law number 5 is what we're going to use kind of first in some sense, because we've got a fraction raised to a power. That's exactly what we have here. And so the first thing we're going to do is use law number 5 to take the power inside the parenthesis. So we're going to take the -3, and distribute it to both individual fractions. And then when we do that, we'll be in the situation where we have law number 4. We have a whole bunch of things inside a parenthesis raised to a power, and then we'll raise them individually. And so I'm going to do 2 laws in one, in other words. I'm going to use law 4 and law 5 to distribute the power to each individual term. And so this becomes x to the -3, y to the -2 to the -3, z to the -3 to the -3, divided by everything on the bottom to the -3. So x squared to the -3, y cubed to the -3, and z to the -4 to the -3. So I've used laws 3 and 4 to do that. And now we've got a bunch of things where powers are raised to a power, right? We've got a bunch of law number 3 here. And so I'm going to go ahead and multiply exponents because we've got powers raised to power. So I'll use law 3 here to simplify it further. And the first one's already simplified, right? X to the -3. Second one will multiply. We've got negatives multiplying, so they become +6. We've got negatives multiplying on the next one, so it becomes +9. We'll have x to the -6, y to the -9, and z to the 12. Okay. Just a couple more steps here. We're making good progress. This particular example has got a lot of the laws in one. So now we're prepared to do law number 2 here, because now we've got things that are being divided with like bases, and so we can use law 2 to subtract the powers on this. But again, just be careful because we've got some more negative exponents. And so when we use law 2, we want to be careful. I'm going to write out the details on this one, just in case you're confused still. So we'll have x to the -3 minus -6, right? So those are going to be added. We'll have y to the 6th minus -9. Those will end up being added as well. And then z to the 9th minus 12. So a few more steps here. Let's do the subtraction. When we add those, we end up adding those, and so we'll have -3 plus 6, which is 3. On the second one, we'll hit 6 plus 9, which is 15. And on the third one, 9 minus 12 is z to the -3. And so that was law, that was just finishing law 2, I guess, I'm sorry. And then last but not least, we want to get rid of the negative exponent. So the last thing we can do is take that negative exponent, use the property up here one more time, and make it into a fraction. And so we can get rid of that negative exponent here by putting it in the denominator. So our final answer would be x cubed y to the 15th over z cubed. All single bases raised to powers with positive exponents. And so that indicates we're done. I would take a minute and try this one. If you want to work with someone around you, that would be a good idea. But at least take a few minutes and try to use the properties that we just learned about or reviewed, and see if you can simplify this one down to a number, two variables raised to two different exponents. Alright, I'm going to keep going with this one. If you're still working on it, feel free to pause the video and finish up before you look at the answer here. Again, it's really, really helpful to work on these as you go. I really hope you're taking this seriously and that you tried that one out and that you continue to do that throughout the course. So in this first one, we've got two individual parentheses raised to powers, and so the first thing we want to do is use law number 4 to distribute the exponents through the parentheses to each individual term. And then when we do that, we'll have powers raised to powers, and we'll multiply the powers. So I'm going to do two steps in one here just to save some space. We're running out of room. So I'm going to use law number 4 to distribute the exponents, and then law number 3 to multiply them together. So we send the 3 through, and don't forget to multiply by the 2 as well, right? It's got to get the 2 as well. And so we'll end up with 2 cubed u squared raised to the 3rd power, so we multiply the 2 and the 3 to get u to the 6th. And then we'll multiply the 3 and the 3 to get v to the 9th. And then we do the same thing on the second one. So we'll have 3 squared u to the minus 6 v squared, right? So we send the 2 through the parenthesis, and it multiplies by the powers. Now, in the second step here, we want to combine like bases. So we've got two u's and two v's, and so we can combine those things together. And when we do so, we'll be in property number 1, where we've got like bases with different powers, and so we'll add the powers. And so we use law number 1 here to add the powers. I'll also multiply, 2 cubed is 8, so I'll do that as well. And then we'll get u to the 6 plus negative 6, right? And then v to the 9 plus 2. And then, I forgot to write down my 3. I've got 3 squared here, so 3 squared is 9. So all these things are being multiplied together, of course. And then we just simplify it down. So I'll multiply the 9 times the 8 first, right? We can multiply numbers together. So 9 times 8 is 72. We'll end up with 6 plus minus 6, so we end up with u to the 0. And then we'll end up with v to the 9 plus 2, which is 11. And so we have 72, u to the 0 we know equals 1, and we know that again from this property here, right? Anything raised to the 0 power is 1, and so u to the 0 becomes 1. And so we have 72 times just v to the 11. And that's the final answer on that one. Okay. On the next page, what we're going to do is talk about radicals. It's totally radical. And so let's just remind ourselves about the notation. So first of all, if we have a square root, we know the square root of a. If we have the square root of a equals b, that's the same thing as saying that when we square b, it equals a. So for example, if we have the square root of 4 equals 2, that means the same thing as saying 4 equals 2 squared. So there's that relationship. The other thing I want to take away from this is, well, let me come back to that in a second actually. Let's look at the nth root before I talk about that. So the nth root is when there's an n inside of that square, of the radical, I mean. And so let's relate that back to the square root, because when there's nothing there, it's kind of like there's a 2 there. And so if you see a root that doesn't have a number, that's a 2. There's a 2 there. It's a square root. If it's something other than a 2, then we call it the nth root, and it looks like this, and we have a similar kind of property. So for example, we could say 3 squared or 3 cubed equals 27. That's the same thing as saying 3 equals the cube root of 27. Or we could go the other way too. We could say the cube root of 8 equaling 2. That means the same thing as 8 equals 2 cubed. And so we have that relationship that goes both ways. And we also have some properties that go along with it. Now, these properties here can be used sometimes, maybe most of the time. But ultimately what we want to do is relate these things back to exponents, which will be done on the next page. But this is still useful at times. So let's go through a few of them. So the first example says if we have two things inside of a root, we can break that root up into two separate roots. So if we have like the cube root of 8 times 27, we can split that up into the cube root of 8 times the cube root of 27 into two separate cubes. And now each one of those is itself a cube based on what we just learned in the previous step here. And so the cube root of 8 is 2, and the cube root of 27 is 3. And so we end up with 2 times 3, which is 6. And so we started with something that wouldn't be able to be simplified unless we split it up into two separate roots and recognize it as those two separate roots, and then that let it simplify down to something nice, which is just 6. We can do a similar thing with fractions. If we have fractions inside of a radical, we can also break it up into two separate radicals. So if we have something like the square root of 16 over 25, we can break that up into square root of 16 over the square root of 25. Those are each perfect squares, and so the square root of 16 is 4, the square root of 25 is 5, and so that simplifies down to 4/5. The next one is kind of like a power raised to the power example. If we have a root inside a root, you multiply the roots. And when we relate it back to exponents, it's literally the x root, like let's say we have the 4th root of the 5th root of 2. That's the same thing as the 4 times 5 root of 2, or the 20th root of 2. Right? So it's how to combine two radicals together when they're inside of each other. The last two have to do with properties of, they're kind of related to each other. They don't come up a lot, but there is one in the homework like this, so you need to be careful about it. The first one says, if we have something raised to the nth power and it's inside an nth root, and n is odd, then whatever's inside there comes out directly. So for example, let's say we have the cube root of minus 2 cubed. Since these are both odd numbers, 3 are both odd, right? Then what comes out is exactly what's inside there, the minus 2. But if we have the same situation, but the root was positive, we get a different answer. So let's say we had the square root of minus 2 squared. Very similar, right? We've got minus 2 inside it in both cases, but in this case we've got an even power and an even root. So in that case, what comes out is positive 2, and let's see why. So for example, if we square minus 2, it becomes positive 4, and then when we take the square root of that, we get 2. And 2 is the absolute value of what was inside there, right? This says what comes out is the absolute value of what's inside there. So 2 is the absolute value of minus 2, which is what was inside there to begin with. And so this relates to number 4 in the exponents homework. I usually get a lot of questions about that one. I try to be very upfront about where to get that answer from. It comes from this one right here. Be careful on that one. And take note, in number 4 in the exponents homework, you're going to have to use this property. Okay, now we're going to talk about simplifying rational expressions, just like we did in the last page with exponents, right? In the last page, we did these examples where we simplified exponents, and we're going to do some examples here where we simplify radicals. But really, what we want to do is use the second method. So this is method number 1, you can see. On the next page is method number 2, which I prefer method number 2. Method number 2 is much easier, I think. It works every time, and if you just know method number 2, it reduces it to an exponent problem, which is nice because you have to remember less things. But this is useful sometimes. And so the way to think about this is one way to simplify radical expressions is to factor out the largest nth root, and then you can combine like roots. So for example, if we had 3 times the square root of 7 minus 4 times the square root of 7. It's kind of like, let me make this a little bit bigger. So it's 3 times square root of 7 minus 4 times square root of 7. It's kind of like we have two like terms. We've got 3 square roots of 7, and we're subtracting 4 square roots of 7. Right? They both have a square root of 7. And so we could think of that as minus 1 square root of 7. The other way to think about it is they both have a square root of 7, and so you can factor out the square root of 7. Right, I factored it out. What's left is 3 minus 4. You subtract 3 minus 4, and you get minus 1 times square root of 7. So if we have two terms that have the same radical, we can basically treat them as variables in some sense and subtract them, right? 3 minus 4 is minus 1. Now sometimes it takes a little work to get it into that form. So let's look at one that takes a little bit more work. So let's say we had square root of 162 minus the square root of 50. We can't combine those outright because they don't have the same radical, right? In the previous example, they both had radical 7. These are two different radicals. But we can use the properties here that we just learned about to break these up and end up using, end up with the same radical, and then we'll be able to combine them. So I can rewrite 162 as 81 times 2, and I can rewrite 50 as 25 times 2. And you can see what I'm doing here is they both have a 2 inside there, so eventually they're both going to have a square root of 2. But first, what I'm going to do is use law number 1 to break the radical into 2 pieces. And so I break each radical into 2 pieces. Square root of 81 times square root of 2 minus square root of 25 times square root of 2. And now we're able to do the square roots of 81 and 25, right? Square root of 81 is 9. Now this is law number 1, by the way. So square root of 81 is 9, square root of 2 is square root of 2, square root of 25 is 5, and square root of 2 stays the same again. And now we have the same situation as above, where we have 2 of the same roots being subtracted. 9 square roots of 2 minus 5 square roots of 2 is 4 square roots of 2. that disappears, will you let me know? It's not a huge deal, but anyway. Okay, so we were talking about exponents last time, and then we switched gears to radicals. We have these properties for radicals, and we did some examples showing how they work, and now we're talking about combining them. And I'll just remind you again that this is method number 1 of combining them, and on the next page we'll very quickly see method number 2. And method number 2 is the sort of the more applicable method that you'll use more than method number 1. So just be aware of that. So let's do one more example of when you might want to use this first method here, method 1. And so we got a couple examples. Those were sort of straightforward using numbers. Let's throw a variable in there and see the types of things that we can do using variables and radicals, excuse me. So if we had something like this, so like the cube root of 8x to the 5th minus the cube root of x squared, as that's written, we can't do anything, right? We can't combine anything because they're two separate radicals that are being subtracted. You may be tempted to use this property and break up some radicals and combine them together, and that's what we're going to look to do eventually, but as written right here, we can't do that subtraction. But we're going to use method number 1 to break up this radical and make it look like this one so that they can be subtracted. So for example, we can rewrite that first radical as 8 times x cubed times x squared. And then if we leave the second one alone, that's good because eventually we'll have just x squareds left inside the cube root, because we'll be able to pull out the 8 and the x cubed. Okay, so this, I haven't really done anything yet. I just rewrote that original thing like this. But now let's use law 1. So by law number 1, we can break this up into 3 separate radicals. So we can get like the cube root of 8 times the cube root of x cubed times the cube root of x squared. And we have values for the cube root of 8. We know that's 2, and we know that the cube root of x cubed is just x. And so those things simplify down. The cube root of 8 becomes 2, the cube root of x cubed becomes x, and then this one just gets repeated. And now it's like we have like terms, because we have 2x cube roots of x squareds, and then we have a minus a regular cube root of x squareds. And so we can, in some sense, do that subtraction, or you can think about it as factoring out the common factor. We can kind of factor that common factor out and get left with 2x minus 1 times the cube root of x squared. So we just factored this out, right? We factored out that common factor here. It's a common factor. So we just pulled it out. And this is kind of going to lead us into the next section too, where we'll kind of remind ourselves what common factors are and factoring and things like that. But you can see the value here is we can use those properties, and we started with 2 things being subtracted, and now we ended up with a factored version of that in some sense. Questions about that at all? All right, let's turn the page and look at the more applicable method here. The method that you'll see more often, the method that you'll see in the homework more often, and give it some practice here. Let's see. Okay. So the first thing this is reminding us about, and I've already emailed some folks about this who've had questions, is that we can change radicals into exponents, and vice versa. Okay, so that's a lot of what goes on in the homework. Anytime there are radicals in your current homework set, the exponent set, you're usually needing to change it into an exponent. And so this is really the big thing in this one. This first part is just kind of showing us a general property that we don't really necessarily need to use that often, but the second one is the really important one. Okay, And so it says if we have a value being raised to a fractional power, we can change that into a radical, or we can change it from a radical into a fractional power. And this is a specific example of that. Okay, so if we have like a to the 1 over n, that's the same thing as the nth root of a. Okay, so the whole point of this box here is really just showing us that any radical can be written as an exponent, and should be, when you're trying to simplify things. So let's just do a couple quick examples here. So for example, let's hone in on this right-hand property. The one that I always use to remember all the other ones is that when you do like a to the 1/2, that's the same thing as the square root of a to the first. Right. So if you're ever trying to remember like what part of the fraction goes in the radical and what part becomes an exponent, I always just remember that 1/2 gives you the square root, because then that's how you can remember that this whatever's in the exponent goes in the numerator, and then whatever is the value of the radical goes in the denominator. So this one is kind of a roadmap for all the other ones, right? So similarly then, if we had like the cube root of x, that's the same thing as x to the 1/3. And we can do that with any number, no matter how high, right? So we can have something kind of silly like the 10th root of 9, right? That's the same thing as 9 to the 1/10. And so you'll see that a little bit in the homework. Especially there's a couple of problems in the homework where it wants you to simplify down some value where it says like 4 to the 3/2 or something like that. And so in those situations you want to change it to a radical and simplify. And then in other situations where it wants you to simplify some big expression, you want to change it from a radical into an exponent and simplify. It depends on, so in other words, whether you go from a radical to an exponent or vice versa depends on the particular problem. Any questions about this concept before we do some examples and look at that? I don't want anyone to get too lost if it's already a little confusing. Is that all right? Okay, so let's look at another example then that's not just a 1 in the numerator, right? Everything in the first line had a 1 in the numerator of the exponent. So let's do one that's like the cube root of 8 squared. Right, we would rewrite that. The exponent inside the radical goes in the numerator, and then the value of the radical goes in the denominator. So this would be 8 to the 2/3. This next one looks a lot like a homework question. It may even be one of your homework questions, depending on what yours looks like. Something like 16 to the minus 1/4. So there are homework questions that look like this that say, simplify the expression or something like that. And it wants you to get it down to some whole number, not whole number, some number that doesn't have an exponent. Geez, let's say that. And so the first thing we want to do on this, right, notice that all of these exponents are positive in the definition, right? All the exponents here are positive. So if we want to use these properties, we need to have a positive exponent. And so we make this negative 1/4 positive by doing what? Yeah, we make a fraction and we put it in the denominator. That's one of the things we talked about last time. Okay, so now it's 1 over 16 to the 1/4. And now, since it's a positive exponent, we can change it into a radical and make it the 4th root of 16. And the 4th root of 16 is a 2, so this becomes 1/2. So 16 to the minus 1/4 is the same thing as 1/2. And so if this is a homework question, it would be wanting you to enter in 1/2. Is that okay? All right. Let me ask you to just think about this one for a quick sec. Actually, let me write down 2 and ask you to think about them. So in this first one, I want you to rewrite it as x raised to some power. And then the second one, I want you to rewrite it as y raised to a power, but there's going to be a few intermediate steps there, or at least one intermediate step. And what I want you to end up with is y raised to some power. All right, so just take a minute and try that. Remember, like, even if you're a little lost, give it a try. You want to look at the properties up here and see how you change exponents into radicals and vice versa. And when you feel comfortable sharing with someone near you, I ask that you please do that. And if you're lost, this is a good opportunity for me to come and point something out, or you can ask a question or something like that. Right, go ahead. We'll just spend, this should only take about maybe a minute or so. Just think about that. So at this point, I'm assuming most people maybe have at least one of the answers. I really do want you to actually talk to the person next to you and see what they're looking at. If you both feel comfortable with that, that's great. If not, maybe someone can help the other person. If someone needs me to help, I'll be happy to do that.
So I just went to CDS.
Oh, that's
here. I don't know what happened. She kind of.
Could I just see one of those pages?
that happens to me in English.
My guess is it probably looks like that.
Really? What page is it?
It's happening.
I did at the library.
That's really important. You might, I know it's a few ways to do, but it's kind of important that you have that stuff down. You can if you want. You have to wait for it to draw that instead of trying to goes real quick, and then you can write on it immediately. No, we use, don't make it. All right, let's take a look at these. Before we look at that answer, I just wanted to point out, this happens occasionally on this stuff. This happened to anyone else yet, where you go to print out the notes and it gives you like some strange stuff? So this is like a future note that was printed out, and she's not the first. I'm sorry, can you remember your name? Sorry? Cynthia had an issue when she printed, and she's not the first one who had this issue. I would just be careful and maybe like test print a page. Do you do it in the library? Do you say that? Has anyone else printed in the library?
Did you do it in the library and that happened? They have to pay for it.
Did you print in the library? Did this happen to you? Okay. And that didn't happen.
I think it depends on the computer.
It's page 21. It shouldn't happen. That's why I saved it as a PDF. Like, this kind of stuff happens when you don't save Word documents as PDFs, but I saved it as a PDF to try to avoid this kind of stuff. So anyway, if I would maybe just test a page. Like, there's math here. Like, this is an equation. This is an equation. Right, this is an equation too. So it's doing it on all the math stuff, not the words. It's doing it on the math. So, and which is important. You need that stuff.
Is that all the page or?
Oh no, it was all.
Yeah, it was all for hers. So, yeah, you may want to bring it up to them. Not that it was super expensive. How much was it in the library? Like $5?
$2.90 something.
$3. Great. That's awesome. Anyway, let's get back to this. So this first one, the square on the inside becomes the numerator, and the 5 becomes the denominator of the fraction, right? So we get x to the 2/5. And then on the other one, the first thing I was thinking that you would do is change the 5/2 to an exponent. So that would be, I'm sorry, change the, I just said it, change the square root of y to the 5th to an exponent, which is 5/2. And then if we wanted to make it y raised to a single power, we could bring it up in the numerator and make it a minus 5/2. Is that okay? Are there questions about either one of those? I'm sorry, what?
Yeah, so like for the homework, so I know you said you could do negative, so that's okay.
Yeah, so, yeah, I was just about to say, like, in general, when you're in homework, and you usually want to not have negative exponents. But I'm just trying to point out that we can go either way with this stuff. You can start with this and go backwards, or you could start with this and go forwards. And it just depends on what you're trying to do in the given equation, really. I was going to say something else, I thought, too. Not sure. Is that okay, though? Are there questions about that? So let's use it in something then. So this is the method number 2, right? Simplifying rational expressions, method number 2. This is the one I like. I think it's just better. I've said that more than once now, and I hope you believe me. And the reason I think it's better is because the previous method, this method, when you're dealing with stuff, first of all, sometimes you have to do this, and that's fine. But if you have a choice, this method requires you knowing a whole bunch of properties about roots. This method, what we do is we change the radicals to exponents, and then we just use the exponent properties that you already know, and that you need to know regardless. And so to me, it just makes more sense to really get good at this method. Okay, so that's what I wrote here. A second method is to simplify a rational expression is to change the radical to an exponent and use the properties from the last page. So for example, if we have like 2 square root of y times 4 fourth roots of y, we can multiply the 2 and the 4 together right now, but that's all we can really do. Because let me ask you this, why can't we combine those together into a single radical? Yeah, they have different roots, exactly. This one's a square root, right? There's like a 2 there. And this one's a 4th root, and they need to be the same in order to put them together. And so this is a perfect time to change the radicals to exponents. And now this looks exactly like an exponent problem that we had in the last section and that you've seen in the homework. Right, so we can multiply the 2 and the, I'm sorry, that should be a 4, not an 8. We'll multiply them together to get 8, but right now it's still 4. We can multiply the 2 and the 4 together to get 8. And then what do we do when we have a like base and different powers? We add them, good. So then we would do our 1/2 plus 1/4. And so this will be our sort of in the middle of another topic, brief review of fractions. If we want to add 2 fractions together, we need to have a like denominator, right? A common denominator. And so the common denominator between 2 and 4 is 4. And so we rewrite the 1/2 as 2 over 4. And then we're able to add them. Because now they have the same denominator. We keep the denominator and we add straight across the fraction. So this will end up being 8y to the 3/4. Or we could write it as a radical as 8 4th root of y cubed. Is that okay? And so again, like if you just do method 2 and change things to exponents, yes, you have to deal with fractions, but that really shouldn't be a problem. But, you know, if you need a little review, you want to come to my office, we can talk about fractions. There's also lots of YouTube videos and stuff out there and whatnot. But as long as we know how to deal with fractions, all we need to know to do this are the exponent properties, which we already need to know anyway. And so that's why I like this one a lot better. So let's do another example. How about the 6th root of a and the 5th root of a. The main reason I'm doing this one is again for a little bit of a fraction review. So when we change those to radicals and we get 1/6 and 1/5, right? And then we want to add them together, it becomes a slightly more challenging fraction problem. But it's still just an adding two fractions problem. Right? And so let me remind you, when you're adding fractions, you can think of a common denominator, or just multiply one of the denominators by whatever the other one is, and then do the same with the other one. Like for example, if we just take the 1/6 and multiply it by the other denominator, 5/5, and then we take the 1/5 and we multiply it by the other denominator, 6/6, we're guaranteed to end up with the common denominator, because we'll have 6 times 5 in the bottom of one and 5 times 6 in the bottom of the other. And so that's going to be the same thing. Right? So if you're ever just racking your brain for a common denominator, just multiply one denominator by whatever the other one is. And we'd end up with the following. So we'll get a to the 5/30 plus 6/30, which is a to the 11/30. Or we could say the 30th root of a to the 11th. Again, kind of strange, but true. Questions about that one? Okay. I'll do one more and then maybe ask you to give one a try here. So let's do this one. Let's do x to the 5th, z to the 10th, all raised to the 1/5. This looks a little more like maybe a homework question. The minus 1/3 on the bottom there. Okay. So when we're thinking about exponent properties that we might want to use here, is anything jumping out to you? So we've got a negative exponent, but I think I said this last time. Generally speaking on these problems, if you're trying to simplify something, you usually want to leave the negative exponents until you can't do anything else. Just because it makes, in my opinion, from my experience, there's less of a chance of making an error. If you really want to move this bottom up to the top, that's okay. I've seen lots of mistakes being made from that. So I'm going to avoid that right now, but just know that you can do that. I was thinking more along the lines of the property that says when we have things being multiplied and they're both raised to a power, we can distribute the exponent, right? So we can take the 1/5 and send it through here, and then we can take the minus 1/3 and send it through here. And the negative 1/3 is going to make those negative, but that's okay. We can still handle the negatives. And then at the very end, if there's any negatives left, we'll get rid of them. All right, so I'm going to write out some of the details to this one. So this one ends up being x to the 5th raised to the 1/5, z to the 10th raised to the 1/5, x cubed raised to the minus 1/3, z to the 6th raised to the minus 1/3. And so that's an exponent property from the last time. And now we have powers raised to powers in all of this. And what do we do when we have powers raised to powers? We multiply them. Good. So do you guys remember how to multiply fractions? You multiply straight across. So like, I'm just going to do the first one. Like 5 times 1/5 equals 5 times 1 over 1 times 5 which is 5. So that was a lot of space just to use that up, but that's okay. You multiply straight across the top of the fraction. So we do like 5 times the numerator is that, and then 5 is the same thing as 5 over 1, and so we have 1 times 5 gives us 5 again. I'm sorry, so we have 5 over 5. Thank you, which is 1. That's better. Remember that? Do we need to say more about multiplying fractions? I'm happy to.
I have a question. If you were to, like that middle step where you have the raised twice again, yeah. If you were to just distribute it and then place that step, what those answers would be, would that cause a problem? A little more complicated? Something?
If you were to distribute what?
Like, for example, instead of x fifth raised to 1/5.
Yep.
If I just have it as x to the 1 right now, would that cause a problem?
No, that's fine. I'm just trying to write out the details. Yeah. If that makes sense to you and you realize you have to multiply, that's great. I just didn't want to write that down and then people say like, how'd that 5 change into a 1? I'm trying to write out some of the details here, yeah. And so then the other one, the z part, if we multiply 10 by 1/5, we're going to end up with a squared, right? Because we do 10 times 1 divided by 5 times 1, which is going to be a 2. Maybe I'll leave it in unsimplified form just to be a little more clear about that. It's 10 over 5, which is 2. And I'll rewrite it in just a second. And then we do the same thing in the bottom. So we'll get x to the minus 3 over 3 and z to the minus 6 over 3. And so all in all, we end up with x to the 1, z squared, divided by x to the minus 1, z to the minus 2. Excuse me.
Sorry, that was a good question. It's going to allow with negative fractions, does the negative go on both the numerator and denominator?
Either, just one of them.
Okay.
Yeah.
It doesn't matter which.
No. It's technically kind of like out in front of it. Yeah. But so the question was, when you multiply this negative by this non-negative, how do you write the negative? So this one, the cubed is not a negative, but the 1/3 is. So the 1/3 brings a single negative with it. If we put it in the numerator and the denominator, they would cancel out.
Yeah.
Other questions? So at this point, I just want to point out, I usually like to say at this point, like you have two options. You have x on the top and x on the bottom, and z on the top and z on the bottom. You can either subtract the powers. That's what I think is the best thing to do. But maybe you want to get rid of the negative exponents at this point. You just want to like defy me and not wait. You just want to do it. That's okay. You can do that. And so I'm going to do it two different ways here. I'm going to do it the subtraction way first. So this could be x to the 1 minus negative 1 and z to the 2 minus negative 2. That's using the subtraction property of exponents. And so we'd get x squared z to the 4th. That's good. Or if you wanted to this step to get rid of the negative exponents, you could bring them both up into the numerator and make them positive. And you would end up with x to the 1 times x to the 1 times z squared times z squared. Right? I just took the ones that are in the bottom and I brought them up to the top to make them not negative anymore. And now you're in this situation, and you'll add them, and you'll get the same answer, right? So I'm just pointing out, like, it's okay if you were thinking about this different. Maybe you went through a different thought process and you wanted to do something else. You can. There's usually more than one way of doing these problems. As long as you're following the properties appropriately, then it's okay. Right? I would recommend doing it this way on the left. This is okay too. But notice that answer if you do it right. Questions? Okay, I'd like to let you try one. Give it a go here. So why don't you simplify down cube root of x times cube root of x squared divided by cube root of x to the 4th. So I want you to get that all the way down into 1x with no negative exponents. And so just to be clear, the first thing you want to do is change them all to exponents. So you'll have 1/3, 2/3, and x to the 4/3. And now you got options. You can do some subtraction. You can combine things on the numerator and add them. Whichever one you choose. All right, give that a go. Spend a couple minutes on that. Feel free to work with your neighbor, and definitely check with your neighbor regardless. That's a non-option. Make sure you check with your neighbor, please. And can I give anyone a hand? A little bit confused of a question, anything like that? Is anyone a little confused about where to start? The nice thing about this one is you already have common denominator, so that's good.
During your last class, by any chance, did you see
When I was there.
during our last class, did you see any binary? I think not. I printed the black notes out after the class. So, but I'll check.
So no mark, mark here, no mark. I would probably end up changing the radicals. I don't remember this.
Could this just be X
I'll look at that. Looks good to me. Yep. All right, let's take a look at this one. So the first thing I was thinking of doing was adding the exponents on the numerator. Did anyone subtract first? You can, but I think the most obvious thing to do is to add the exponents. And so we'll end up with x to the 3/3 divided by 4/3. Whoops, x to the 4/3. And then you subtract. And so we'll get x to the minus 1/3, which is 1 over x to the 1/3, or 1 over cube root of x. Either one of those is fine. Whoops. As long as it doesn't have a negative exponent, that's good. Questions about that one? Okay. So let's look at one of the homework questions. I know there's still some questions about those. So let's take a look at one. I got to grab another piece of paper. Gotta snag a piece of paper for one of you fine folks. So I'm going to try to do not the exact problem. I'm not going to finish it either, but get you started on this. So this is the exponents homework, number 7. And it says something like this. Cube root of some big number. I'm going to make it 9042. And then you got some variables in there. Let's make it like g to the 5th y squared. And then it's being multiplied by a square root of the same large number times some other variables with different powers. And so again, yours will be different than this, but the same, it looks the same. And the question is, simplify it down to as much as possible, and it wants you just to enter in the powers of the exponents and the constant, right? So based on what we talked about today, what's the first step? Yes, take the radicals and change them into exponents. So we do this, and we make it into a 1/3. Right? It's all inside there, so the whole thing is raised to the 1/3 and the 1/2. And so now this looks a lot like an exponent problem. It is an exponent problem, right? So we'll keep going just a little bit with this. So then at this point we want to distribute the exponents, right? We take the 1/3 and we send it through like that. And we will end up with the following. We'll get 9042 raised to the 1/3, g to the 5/3, and y to the 2/3. And then we'll get 9042 to the 1/2, g to the 2/2, y to the 1/2. Don't forget to apply the radical to the constant, right? It goes to the big number as well. Don't forget that. Is that okay? So what's the next step? Combining the like terms, and what are we going to do with the exponents? We're going to add them. Good. So then I'm just going to stop at this last step here, which is virtually the end. You add the exponents with the 9042. You add the exponents with the g. You'll need to find a common denominator. And you add the exponents of the y. And so I'll let you finish that, but you just need to find a common denominator for those things and then add them together. And again, yours is going to look different. I just made that one up, but it looks very, very similar to that. Is this the one you were talking about yesterday, too? So you can go tell your friend. She's going to be so excited. Did you try that? Were you not trying that? Okay. Okay, good. Are there other homework questions other than that one?
Yeah, there's one that says 12
All right. Everyone listen up. I've said this one, no offense. I've said it 3 times now. I will say it a 4th time. This is number 4, right? It's number 4. When you have an even root and you have a thing raised to that same even power, whatever comes out is also going to have an even power. So even 1, even 2, you'll end up with another even 3. But what's missing? You need an absolute value around the side of it. Because we have the property that says when you have an even root and an even power, you need absolute value around it. So whatever your answer was 5 probably, right? B to the 5 or something like that? Is that because you had 60 and 12? Is that what it was? So you want to just put an absolute value around your answer, and that'll be it. Okay, we had that on the oh, it was a radical property. I have it right here. It's this property right here. When you have an even root and an even exponent in the root, you need an absolute value around it when it comes out. The idea is you can plug a negative into that a, but the even root's going to make it positive, and so it's always going to come out positive. That's the reason that you need the absolute value around it. Is that okay?
Yep.
Other questions? Homework questions?
You still put an absolute value even if the answer has a non-exponent, right?
Even well, it'll have an exponent of 1. Is that what you mean? Like if it was like
Yeah. So the answer would be
like if it was like square root of x squared or something like that, you get x. It's x to the 1, and you still need an absolute value. Yeah.
There's one question that I got on my work that's like it gave you like the 10th root of the 50th power, and it just says the expression.
I'm sorry, but I have no idea what you're talking about. If you want to pull that question up, I'd be happy to look at it.
Yeah, right now.
Yes. Does anyone have a question that they have in front of them that they want to ask? This is that problem. Yeah. Right, the expression this equals blank.
yeah. How did I not see that?
I don't know.
Alright, well, I'm myself.
You hang your head. No, I'm just kidding. Great. So hopefully we're squared away with problem 4. I always like toy with just deleting that one because I do this every semester. Like there's just so much confusion about question number 4, which makes me think it's kind of a good question. I don't know. Maybe anyway.